Okay, Jill. And Kyle, give me the other name.
Okay. Jill and Kyle have money to deposit in the bank. Okay, Jill has $100. Kyle has $1,000. Yeah. The bank offers a 10% rate of interest. After 1 year, will you find out how much Jill has and how much Kyle has? And this is a 10% annual interest. After 1 year, it's not monthly, it's annually. The interest is compounded annually. What? We only do the first year so far. First year, how much does Jill end up having? Okay. And how much does Kyle have? Okay, so tell me how you did that. Okay, so that's one way to do it. Can you do a more concise mathematical formula for that? How do you find 10% of 100? Yeah, 0.1. You take, let's go down here. Where did I want to do this one? You do 1.1. No, the 10% is 0.10, which is the rate, and you times it by the amount you have. We'll call that Y. The amount invested is Y. Okay? And it equals the rate that your money is increasing over time. What do you think we call the rate that the money is increasing over time? The money increasing over time. And money is Y, dy d over time, dt. dy dt. So dy dt is a rate, and Y is the money invested. So after 2 years, kind of a good question. Do we just add another $10 to Jill, or just now we put interest based off of the first year's ending balance? And it compounds after the first year. So 110 increased by another 10% would be, what's 10% of 110? $11. So you just move the decimal once. And $11, so if we add 11, we get 121. How much would Kyle have after the second year? Yep. Add it, $110, 1,210. Okay, so I want to know how much money they will have in 20 years. In 20 years, we have dy dt equals any rate. This is the general formula. Equals a rate K times the amount that they invest. Okay? And the K is any rate. Okay, before we start plugging things in, first, make sure you know the general form, what you're writing. First, write the general form. So without plugging in information that you know. So I want to know how much money they will have in 20 years. And then this is calculus class. What do you think we would do to find the amount of money they would have after 20 years? Okay, what are you trying to do? Okay, close. Why do you want to move DT over? So you move DT over. Once you do that, times by DT times by DT, great. D1 by itself, we have KY DT. Sure, we can integrate the left, but we can't integrate the right. But unless we know how to integrate by partials. Okay, so what do we have to fix on the right-hand side? And move this Y over to the Y side. We have two diagrams, and one has to be on one side to indicate, the other has to be on the other side. And we know which side they belong based off the dy and the dt. So we divide by the y. So we have 1 over y dy equals k, some constant, dt. And then, yes, we can integrate both sides. If we integrate 1 over y dy, John, what do we get? Good. Okay, equals, if we integrate k dt, derivative will be 0. Integrate. We get k t. And what are we missing here? Plus c. Since we're trying to find the amount that we'll have in 20 years, we're going to put the plus c on the right-hand side because we're going to solve for y. We don't want to solve for time. We know time will be 20. We're going to solve for y, get y by itself. But before, we're not putting in things yet. How do we, remember this one has a c and this one has a c, but we can combine them into one c, right? Okay, how do we solve for y? Yeah, we have to e both sides. Now, e everything, that whole thing, and this whole thing. So the e and the natural y cancel out, leaving just y equals e to the kt plus c. Okay, I'm running out of room, so I'm going to do my little arrow. Y equals e to the kt. Isn't this the same as times e to the c? We just did one of these actually on the intervals. When you multiply times the same base, you add an exponent. So kt plus c was the addition. So we separate them with multiplication. And e to the, my book has mine, e to the c is what? No, not 0. It's a constant c. 2 point, I was right, if it's 1771 on e. But this is a number raised to a constant, it's still a constant. So a constant can come out front, big C, e to the kt. Have you seen this before? Okay, no, you haven't seen it before? Maybe have you seen it in this one? Perch, right? You guys have done perch before. Sometimes there's a bunch of different forms it all comes in. What does this little, especially you in physics, you probably know this. What does that little zero mean? Not initial. So this is the initial principle, final principle. The principle is the amount you insert into the bank at the beginning. Initial, final. So that constant would be the initial, and the y is the final. Let's see, there's one other way you can see this. A equals purge. Okay, so all of these ways are the same general form. Probably more familiar with the put. Okay, so now let's actually answer the question. I don't know how much they will have in 20 years. Okay, and they were told in terms of y. The money invested was y. So we're going to use this form. E to the K, G, well, or RG. You can use K's or R's. They know we're using K's, so. Okay. What do we know that we can plug in for this problem? We know the time. T is time, right? And then we know that. Okay, so we know why not. How much was the initial investment? We're going to have to do it for each person. Investment. So we had Jill. The initial investment was what, $100? E to the time we knew was 20. And for Kyle, the initial investment, $1,000. E to the, again, time is 20. Anything else we know? Yeah, we know the rate is 10%, but we can't just type in 10%. We have to write an investment form, which is 0.10. 0.10. And this will give us y. What does y represent? Yeah, or year-end. Year-end money. So I think you guys can calculate now, and this, we'll go ahead and use a calculator. Make sure that you group, if there's multiple things in the exponent, you need to group those together. If there's multiple things in the exponent, you need to group those together. Okay, so after 20 years, how much will Jill have? $0.91. So money, we're allowed to go to a penny. And make sure you put a dollar sign, because that's the unit. And approximately, because it's rounded. Okay. How much will Kyle have? I don't think it's 6 cents. Oh, yeah, 0.6. Yeah. No, so they're almost exactly the same. They're just one place value off, right? Because of the 100 versus 1,000. Okay. What? Here's a constant. What? Okay. Keep thinking about it. When will their money double? So, again, two different situations. We have Jill and Kyle. Now, if Jill's money is doubling, how much would she have in the end? What? Okay, but we know she starts with 100, so 200. So 2 times 100. Or you can put 200 if you want, but let's see what happens. Equals the 100 e to, do we know the rate? Do we know the time? No, that's what we're looking for. When will it double? And the reason I have that as 2 times 100 is because right here, if I'm solving for t, we get it by itself. So move the loose ends first. Divide by 100, divide by 100, and so my 100's already there. So 2 equals e to the 0.10 t. So can you guys solve for when will her money double? Yeah, you have to think, how do you get the t out of the exponent? Rebecca, what did you do on those sides? Natural log. That's the inverse of the e, right? Oh, bring that down. Natural log, extreme natural log, everything to a natural log. All that, the e natural log cancel out, bringing the exponent down. Natural log 2, divide by 0.10, divide by 0.10. So, approximately when, in years, because our time was in years, approximately when will it be doubled? Now, it doesn't say when you get held around, so I'd probably go with 6.931 years. Okay? Find the same for Kyle. When would Kyle's money double? Instead of starting with $1,000, instead of starting with $100, he's starting with $1,000. Yeah. You know what's going to happen? 2 times 1,000 equals 1,000 e to the 0.10t. Everything else is the same except for the 1,000, right? And 1,000 cancels. So, once you cancel that out, these steps are the same. So the answer is 6.931 years. Flip it over. Yeah. Okay. Flip it over. The bacteria in a certain culture increases continuously at a rate directly proportional to the number present. Okay. By a differential equation to represent the problem. Differential. So we should have something that looks like a derivative, maybe. Differential equation that represents the problem of this bacteria increasing continuously at a rate directly proportional. We've actually written this equation earlier. Does anyone know what we write? Well, it's not dy dx, it's dy dt equals ky. If there is initially 400 bacteria find P of T in terms of K and T. Okay, what does P of T represent, do you think? When we're finding P of T, we get this number, what does that represent? Good, so can we call it population over time? And it can be at any time, depending what time we're plugging in. Okay, so again, starting with a differential equation, dy dt equals ky. This is the last one to make you derive it, but getting into the form where it's P of T equals. So how did we do that last time? Because we want to know the population over time. How do we get it into the form where we can solve for P of T? Yep, we have to get our variables separated. So we need the T's on one side, and the Y's on the other side. Okay, what else do we need to do? We need the Y on the left. And notice the dy and dt, they're in the denominator. We don't want them in the denominator. They should be in the numerator position. Okay? Now, when you integrate these, we already know when we integrate, well, show step by step, and then it should look familiar. Good. Okay. So see, most of those are the natural log of y, absolute value y, equals kt plus c. And you leave both sides. You have y equals e to the kt plus c. Okay, where does the c go? We split it up. Where's the c going to go? Not go away. E to the c is a big constant c. E to the kt. And we can replace the y with what they want our notation to be P of t, population over time. Okay, I boxed that, but that's not the answer. That's just the formula. Okay, now that we have that population over time, okay, what do we know we can plug into to find the initial form of bacteria? Find P of T in terms of K and T. Meaning K and T should still be in your equation. And it says in terms of K and T, those letters should still be in the equation. Yep. So, do we know P and T? No. Do we know C? Yeah, C is 100. E is a number. Do we know K and T? No. So this is the population over time, at any time, when the initial bacteria is 400. Yeah. Okay, now down below in part C, if the number of bacteria triples in 6 hours, how much bacteria will there be in 12 hours? Okay, so with your group, I want you to walk through that. If Still talking about the same bacteria. If the bacteria triples in 6 hours, how many bacteria will there be in 12 hours? Okay. Brainstorm with your group. How would you solve that? Show all your steps now. I know you can do some in your head, but practice showing the steps. Keep in mind that this is story problems, so make sure you explain what your answer means. Four decimal places. And keep in mind this needs to go exponentially, so it doesn't mean it has a continuous, it doesn't go necessarily proportionally. So sometimes it's appropriate to round, other times it's not. Because on the first part, you definitely need to round to 4 decimal places. But then, like he said, does it make sense to have a decimal form of a bacteria?
Triples in 6 hours will be 1,200. 6 hours.
We should this way. You can make sure it makes sense in your head by doing that, but I don't think this way. Okay, you can type it up to the board and explain and show you what you guys did for the first half and why you had to do that. I think pretty much everyone's on the same page. But. And initially there's 400 bacteria, and it triples after 6 hours. So after 6 hours, how much would there be? So the population over time, P of T, you replace with what? Population over time becomes this is the number you just told me because it triples, yeah, 1,200. Not to the line tool on the skinny yet. I wish it would just stay square. You had my other board, the smaller smart board, you have the problem. It's the wide smart board. That one I could go anywhere. Okay, now you have two variables, but E is a number, but you have K and T. One of those we know. Which one do we know? The time, yeah. So the whole goal for the beginning is just to solve for which variable? Just, yeah, tap outside. So change the T to a 6, because that's our time. So in the very beginning, you have to find what, Anisha? What's the first half of the problem? Okay, the rate. Once you know the rate, then you can figure out how much bacteria will be left over after 12 hours. Okay, so to solve for the K, energy needs to move away from 400E to the, Good. You can use this, if you scroll down on the left-hand side, you'll get more space, and you can go down to the next band page, you'll get more space again. You should use squiggly, because if you round it, the decimal goes on forever. So squiggly equal signs, because you're rounding. Cool. Okay, Ethan, will you go take that rate and show us, thank you, Alex, show us what you do to find 12, how many bacteria would be after 12 years. Yeah, and maybe scroll back up to the top of this section. Yeah, and then you can just do it on the right-hand side. good. So when you plug back in, which this time you don't know P of T, so we're solving for, but you do now know the rate. So you replace the rate. And then can we say in how many years? 3,600 bacteria in. Great, thank you. Yeah, approximately. Well, it is quickly. Is it hours? Oh, it is hours, yeah. Okay. Alright, number 3, turn it over to the next page. I am going through this whole thing with your group. Now, I've seen a few. In 1998, I was interested, I was in 8th grade, but apparently I was interested in Mars. In 1998, I was interested in finding out if there was life on Mars. I found out there was actually 18 Martians living on Mars. Do you know they're going to send people to Mars, like live there for the rest of their life? Actually, that guy, he was on the list of one of the finalists to do that. He was kind of interesting. But maybe, yeah, I don't want to go over this one. If you never see your family or friends or any, again, you'd be in history, but maybe I was like 89 years old. I heard the other day that in 2013 we're back to 59 Martians, so we're really 18, and now there are 59 Martians. So we're going to go through what is the rate of growth graph, and you've been hired as a scientist to do, just A and B is the only part for number 3, then 4 is different. So with your group, find the rate of growth of the Martians, the Martian population, and then graph the exponential function that represents their rate of growth. So think of what's the variable you're solving for when asked for what's the rate of growth. Change that to hours.
So, you know that after some pretty stuff, started with 18 Martians, so that's going to be our C. And then our PG is going to be it.
Make sure the shorter problems, you're explaining what these numbers are that you're getting. And if you're rounding, you shouldn't be putting an equal sign. You should be putting an approximation symbol. Yeah. Okay, Alex, you didn't push one up last time. Let me pick someone to go do A, and I'll have Ethan pick someone to go do B. Read? Okay. Come up, read, please. Okay, and please explain why you're up there. So that's always a good place to start, is with your general form. After so many years, right, after time. I went round until the very end, because otherwise we're going to get rounding error. So I would keep it actually about fraction. Right? Did you keep it in if you're any chance? Okay. I just want to see if you get something different besides because he rounded at the beginning. Yep, that'll work. Now, what does this mean? Can we write this in a sentence when we get a number? What does this mean? Stand by for a second, you can write the sentence. You guys out here. How would you explain what this number means? Okay. Per day? Per year. So, we would say the yearly growth rate of the Martian population is this, or 0.0791 is the approximate rate at which the Martians increase per year. Martian population increases per year, or the rate of growth is about 0.0791. Because you do there's a difference between growth and decay, right? And this guy specifically asks for rate of growth. So I would definitely say rate of growth. Yeah. Okay, good. Thank you. And who's going up for part B, Ethan? John, go graph that, please. Okay. Okay, this is shown as back in time, though. What's our initial time? T equals 0. And how many Martians are at T equals 0? Okay, then we know another point on the graph. So, yeah, time is 15. Where would the point be on the graph? Yeah, so you need your scalings off a little bit. You need to bring it, no, that 15 is fine. You really just need to bring that 15 down. Because 59 is up on the ceiling the way you graphed it. Could there ever, and arrows, could there ever be negative Martians? No. And on the left side an arrow as well. Because at some point there are probably less than 18 Martians, but we have a vertical, horizontal asymptote. Y equals 0. Okay, this time I want you to take your calculator and a pencil, stand up, and you're going to pick one different person that's not on your current group to work with. And one of them will have to be a 3. Okay, stand up, and there's plenty of groups around to find a new place. Find someone who's not in your group to work with. We'll have one group of 3. Okay, and go to your number 4 together. And only do 4, don't go on to 5, please.
Okay, so let's everyone look up at the board really quick to make sure.
I think we kind of eventually got on the same track. And then talk to each group about storing. Since that rate is not your final answer, I would not cut it off. I would store it, and then, yeah, I showed you that. So always start with the original. Whether you use P or C, I really don't think it matters. But punch is kind of easy to remember. The initial, we don't know, right? And we don't know the initial rate for the half-life. But we do know the time for the half-life. What was the time for the half-life? 57. Now, P of T is the population over time. Beginning with half-life, it would be half of the initial population. If you use C's instead of those P's, they'll do the same thing. So those P naughts cancel out. So even though there's two that we don't know, those P naughts cancel out so that we only have one variable that we don't know now. Okay, so natural log both sides, I think we've basically all got here. Natural log 1/2. So those cancel out, we have R times 5700. So the rate, now this was interesting, because it was, I guess, that one's equal. We got scientific notation on our calculator. K, what does e to the negative 4 mean for the decimal? Move the decimal 4 places to the left. Because when the exponent is negative, it should be a really small decimal. Okay? So, this is your rate. I would store it as a, did I get around to every group? I think I told every group. Is every group able to store it as K? So I'm probably need to do it on this calculator. Natural log 0.5 divided by 5700. Make sure you close that parenthesis before you divide by 5700. Store, and I choose K because we're calling it K, alpha K. And then anytime you type in the alpha K, it will program this number in. Okay, you can call it K. Alright, again, you always start with the general form. In RK, whatever. Okay. Okay, the initial is P naught still. The time is what we're looking for. We now know the rate that K is that decimal down there. We're solving for the time. What would the P be on the left? We want 90% of P naught, or C, if you guys are doing the C. So, same thing as P naught, even though we don't know it, they cancel out. So, don't forget that there are two unknown variables. E to the we know K, we don't know T. Natural log both sides, so we get natural log 0.90 equals KT divided by the K. It's programmed into our calculators. So the time, what's the time if we have that programmed in? Oops, I hit a plus sign on that set. What did you get? Okay. 866.4176. What is this? Years. And this one was rounded, so I'm going to put the approximation rule. That store button is really useful. Because you're going to have rounding out and start rounding too early. The store button is right above the on button. So someone to store this, that's what we're using again. You go store, and then it says an arrow, and then put the letter you want to store as. So use the alpha, the green, and then pick a letter. And enter. And next time I use it, like I use it here, And then natural log 0.9 divided by the K. And I use alpha K to do. Alpha K. That's how you use it. Okay? Alright. Your homework is this pink sheet as it's stored in the middle of this paper because I copied the answers, so I cut them off. Okay? So I want to do this on a separate piece of paper, but it's exponential growth and decay practice problems. I need one more. Tuesday. No, this one's that. That means you want to answer it? Okay, but we have our, after school today, we have AP pre-response question practice, and on Friday we have the 100% derivative test. If you answer the first time and you're wearing cookie, don't forget those plus C's. Integral test, that's a derivative, the rest, integral test. If you answer the first time, then you're done.